Thanks for the warm welcome we've received so far. That's very nice. It's very promising. So MAROON-X is a radio velocity spectrograph that we are currently building in Chicago. And as you can see from the crossed out Magellan, originally that instrument was intended to go to a 6.5 meter in Chile. And we now are basically retrofitting that instrument to come to Gemini instead. So I hope during this talk I won't use the word Magellan too often in the wrong context. So forgive me if I do. Some things are just imprinted in your spine after a while. So what is MAROON-X? MAROON-X is a radio velocity spectrograph that serves primarily one target, and that is the observation of M dwarfs. And what is my... Okay. So M dwarfs are presenting a very interesting shortcut to finding another Earth-like planet in a reasonably short time now. So M dwarfs are interesting because they are much lower in mass. So that means that any reflex motion, both in radial velocity and in astrometry, if you will, from a given planet around that star will be much higher. So it's much easier to detect a signal from an Earth mass planet around an M dwarf. The other thing is that M dwarfs are much fainter than the Sun. So a planet that would orbit in a much closer orbit around an M dwarf can still be in the habitable zone, where at a solar type star you wouldn't be in the habitable zone anymore. And again, a planet that orbits in a smaller orbit is easier to detect with radio velocity, for example, and has a much higher transiting probability. So it's much easier to actually find a transiting one, and that will then enable us to actually characterize its atmosphere and eventually look for biomarkers, for example. So there are a number of transit surveys out there, both in space, K2 and the upcoming TESS mission, of course, but also quite a number of ground-based surveys. And so delivering follow-up, both in terms of confirmation of signals, but most importantly, mass measurements of candidates coming from these transit surveys is the prime goal for this instrument. So this means that we are doing target vetting for upcoming atmospheric studies on these transiting planets that we want to do with HST, Spitzer, and James Webb in the future. And since we, for a transiting Earth-like planet around an M dwarf, we will still have to stare, even with James Webb, a long, long time on such a planet to get a decent signal to determine whether that planet in its atmosphere has water, oxygen, etc. We really have to be sure that the planet we are looking at and that we're dedicating a lot of observing time to is actually what we expect it to be, a rocky Earth mass-like planet. And so target vetting is very important, so we are not wasting a lot of time and finding out after the fact, oops, that looked like an Earth-like planet, but it's actually not. So the key requirements for the instrument basically flow down from the scientific requirements I just said. So if we are looking at what is the habitable zone for a 0.15 solar mass star, we basically see that's at 0.055 astronomical units, and that gives us roughly a 12-day period. So that's roughly the periods we expect. And then we can say, so one Earth mass planet in this orbit, what's the radio velocity amplitude? And we find, well, it's roughly 1 meter per second. And so based on the Kepler statistics, we expect that TESS will find about 20 planets with radii smaller than 2 Earth radii around mid-M dwarfs in the solar neighborhood. But typically, the statistically expected first planet out there is still pretty far away. It's I forgot what it is, but it is within 20 parsec, but it's not in the immediate solar neighborhood. So we still would deal with a host star that is only 16th, 17th magnitude in V. So that basically sets the overarching science goals and the overarching specs for the instrument, which is basically we have to be able to measure a meter per second on sky for a 16.5 VM dwarf in 30 minutes or less. And so basically we ask ourselves, so where do you have to go to make this measurement to be able to get that? And a couple of years ago, a number of studies came out that looked into what wavelength range we actually want to go to do that. And most of these studies were actually based on theoretical spectra, so on models of how M-dwarf spectra will look like at high resolving power. And that's a little bit dicey because we don't have that many examples of how M-dwarf spectra actually look like at that spectral resolving power. So we basically collected the few examples that were available from instruments like HARPS, UVIS, CRIRIS, and basically looked at an actual spectrum and simulated what the instrument performance will be. And so on a 6.5 meter telescope, like the Magellan telescope, with your, the numbers we anticipated for the instrument and both the models and the observed spectra, that is basically what you get. So these are chunks of 100 nanometers, and that's essentially the collectible radio velocity information that is intrinsic to the stellar spectrum. And so this will look roughly similar for Gemini because we have a larger aperture, but on the other hand, with the same size instrument, we have a slightly smaller field of view, but we are also more sensitive because of your silver coating on the mirrors. So these numbers will hold both for the originally intended place in Magellan and for Gemini. And we basically see that in the red optical, if you basically combine the light from 500 to 900 nanometers, you basically get down to an intrinsic 0.7 meter per second or so radio velocity content. And going further blue, you basically lose very quickly because the stars become so faint in that region. Now, going further red, and that's what has been suggested in the past to do this in the infrared, yes, there's much more light, and there are also still a lot of lines, but it becomes much more expensive to do that there. So we came to the conclusion that in terms of cost-benefit ratio, staying in the optical, but going out of the visual, but then towards the infrared, that's basically the sweet spot we want to be. The tricky part is, of course, the Earth atmosphere, and that's basically shown above here. Where is the Earth atmosphere transparent? And so we are starting to lose certain band passes here, and there are regions where it's basically hopeless to do this from the ground. And this is factored into these numbers. We are very conservative here and said, well, we assume we cannot do anything about the telluric line. So anywhere where telluric lines are that are deeper than 10% within plus minus 30 kilometers per second, so within the barycentric motion span, we have to assume that spectrum is lost, that spectral coverage. So these are basically the fractions that are left in these bands that are then still available for measurements. So we convinced ourselves that this is actually the best spectral coverage that we want to build an instrument for. And so the conceptual pillars for the instrument are that we wanted a fast and sensitive instrument, that it still has to be affordable for a large aperture telescope, that we have to work on an accelerated development timescale because we wanted to be ready with MAROON-X once TESS is coming online, because that's kind of the driving force for doing test follow-up for us. And we have to work with a small team size. So we basically working in an approach that I think is relatively rare in this business. We outsourcing everything to commercial partners where we think this is feasible and makes sense. And then we develop the parts that you cannot simply buy and that you cannot trust a vendor to come up with in-house. And so for radio velocities, that's particularly tricky, because a lot of problems to get to 1 meter per second or below in terms of instrument stability, this is a highly coupled problem. So for example, the thermomechanical stability of the core spectrograph that you would have to spec out and give to a vendor is of course highly coupled with, well, in what environment will you put that spectrograph? How well can you control the temperature, for example, in the room where the spectrograph will be located? The same is true for questions like optical robustness, that what we would call to pupil illumination variations, meaning during your observation from a fiber-fed spectrograph, your fiber will slightly move. That means that you will see slightly varying focal ratio degradation, meaning the size of the cone of light coming out of your fiber at the spectrograph will slightly vary over time. And that in terms means your pupil illumination in the spectrograph will change, and that will give you a change in the line spread function. And so you see there are a lot of coupled problems that you have to deal with. and that you have to make certain assumptions on very early on to set your specs for the parts of the instrument that you outsource. And of course, then you basically have to ask yourself, what in terms of calibration, what do you want to do? And we basically decided to build a Pupil ettalon, a white light ettalon that is traced with a rubidium cell, and that you will see later gives you basically a comb-like spectrum that you would otherwise expect from a laser frequency comb. But we were able to actually build that in-house to a fraction of the cost what a laser frequency comb would cost. So we think we have an extremely stable and high density wavelength calibrator that will offset maybe some of the shortcomings that we would encounter in the build phase, so to speak, of the spectrograph. So in other words, if our temperature stability is not as good as we had hoped, I think we can recover from that. But of course, you want to push that to the very latest stage. You don't want to inbuild that right in the beginning and say, doesn't matter, we have a good calibrator. So that is still something that we will see in the lab before we deliver the instrument, where we actually are with that. And there's one small word down there, software, and that basically is a misrepresentation, because you can have a talk about this in and by itself. This is as important as the hardware in this game. So making use of all that information, especially from a high density calibrator, is not an easy problem. So it's not your simple like, oh, let's reduce that to a 1D spectrum and you're done kind of thing. This is really at the end a very complex software package. And if you look at other instruments like harps, for example, where this is kind of a black box and there's a radial velocity number falling out, there's a lot of work that went into this. And so we hope to find smarter ways to do things, and we will also not be as protective as, for example, the harps team about their software. So ours will be available to the public. But again, this is a major part of this work, although it's just a small word down there. So as I said, we try to outsource as much as we can, and we came to the conclusion that the best way possible is to actually buy an initial spectrograph from a company. And so back at the day when we decided how to approach this project, Kiwistar at Callahan came up and said, well, we have a good design for a 100mm initial spectrograph that would be extremely compact, and we would be open to modify the design on this to your needs. And so that's the route we went. And then we kept the development of all the other components at UChicago. So we built and characterized fibers of different shapes. We built a pupil slicer and double scrambler, the wavelength calibrator I already talked a little bit about, an environmental enclosure, and we started working on the software. So these are all the things that we started on working at UChicago while the spectrograph itself was built in New Zealand. So the core spectrograph, the basic numbers, it's your classical wide pupil design. It has a 100mm beam on the shell, but then a 1 to 3, so very strong beam compression before it goes out to the cross dispersers. So you only have a 30mm diameter beam going into the camera arms. There are two arms. One is covering 500 to 670 nanometers, the other 650 to 900. So you have a slight overlap to basically cover the part where your dichroic closes and opens. So you have this region basically twice. We work with very efficient VPH grisms as the cross dispersers. And so we had to make a compromise, again, for cost reasons, in terms of how well we will stabilize this instrument. And so we decided that we will only put the main optics in vacuum. So the shell grating, the collimator, all these parts, the fiber feed itself, this is all within a vacuum chamber. But the cross disperser and camera optics are actually just in a hermetically sealed barrel outside of the vacuum chamber. That makes the chamber extremely compact. And when you run the numbers, you see that you actually don't need kind of a vacuum level pressure and also temperature stability on the camera optics. And so this is kind of allowable, but you have a certain risk here that your interface between the vacuum chamber and the camera arms itself might make you vulnerable in terms of radial velocity stability. There was an intensive trade-off study what base material we would use. So there's this common perception that, oh, if you want something stable, you make it an invar. But it turns out that this is not as easy as it sounds. One thing is that because you have to use invert and everywhere, you have a problem with mounting lenses in invar barrels because of the gross mismatch of the CDEs. And so transporting that camera barrel, for example, making sure that during the temperature swings it will see during shipping, nothing breaks, is not so easy. And machining invar is not so easy. If you do it wrong, you actually make it worse than with classical, like stainless steel, for example. So we came out with saying, we actually build everything in stainless steel, all the structural components, and use invar only where it is necessary and where we are sure that we know how to machine it. And so I think that turned out very well. So the optical design is shown here. We basically have front optics that convert an F5 fiber input to an F10 beam that is then accepted by the spectrograph. You have your main collimator, 1 meter focal length here, R4 is shell grading. You have your secondary collimator here that affords the 1 to 3 beam compression. And then with the dichroic, you go out into your 2 camera arms for the blue and red camera and have your detectors at the very end. So that in a 3D sketch, now, sorry, this is all flipped now in X, this is how it looks like. So this is your vacuum chamber, top lid open, main collimator, grading here, and your camera arms and detector systems outside. So one of the main upgrades, so to speak, we did on the design for this instrument is to have all the pupil relay and the slicer, so everything that has to do with the actual input slit in vacuum and directly coupled to the internal optical bench. That was different in their previous optical design, their prototype instrument that they built. And this will allow us, I think, very high stability with that instrument. So the slit format for MAROON-X looks a little bit funky. So our slit is comprised out of 5 rectangular fibers. That's an actual image of a prototype of the slit I built. So you have 3 fibers in the middle that will contain the starlight. You have 1 fiber for the skylight and 1 fiber for the calibration light. So you have simultaneous calibration with your spectrum. These fibers then form the slit, and they have a width of 50 micron. But the whole slit is really long. It's really 2.7 millimeter at F10 at the input of the spectrograph, which for an Echelle spectrograph is really large, like tall slit. On the detector, this will look like this. All the individual traces per order are really separated, so you can extract the spectrum separately. It's not that they are overlapping or whatever. We will see later an actual image how this looks like. So we have intensively looked at simulations for the camera performance. Julian, who is in the room here, has written a code to actually work with CMAX to then show you how the point spread function across the field, in this case for the blue camera, look like. And then in color, you have encoded here what the encircled energy radius in micron is at various positions in the field. And then we can look at this for the different positions in the slit. And this basically fulfills our specs where we set the encircled energy radius, in this case in dispersion direction, should be smaller than one pixel. And so that's basically fulfilled until you go to the very edge of your spectral format, where you basically already have overlap then with the red camera. And the same is true, although we are closer to the minimum specs here for the red camera. So ignoring a little bit this corner here, which is just an artifact of how things are plotted, we are basically filling with the 2 CCD detectors the full format of both cameras. We only lose a little bit of the free spectral range of the reddest borders in the reddest camera, just because they're becoming too wide. But the loss is very, very small. Another thing that we paid attention to is to have a very efficient instrument. Because again, we are on a large telescope, but on the other hand, the stars are very faint. And so efficiency was one of the main goals. And so what we did is we basically set a minimum spec. You see the blue and the red arm again here, efficiency on the y-axis, wavelength on the x-axis, a minimum spec and kind of a goal spec in both cases. And since we right now have the blue arm built and integrated, we can basically look where we are, and we actually find that the S-build, which is the solid curve here, is in most cases at the level of the goal, and at some points even slightly above our goal level. And one of the reasons why this is that we actually got a shell that has a protected silver coating instead of an aluminum coating. So you find actually peak efficiencies at the 85% level or so for the shell grading, which is very gratifying. So for our wavelength range, that makes a huge difference. And that basically allows us to achieve efficiencies of the core instrument, meaning from the virtual input slit to the CCD, in the blue arm of above 60%. And we hope that with the red arm, which will be built this year, we will also reach about 60% or so. So for the red arm, which is not built right now, these are basically projections updated with the components that are already existing. But we hope that we basically really land up here as well. And that probably mainly right now depends on the question how good the cross disperser will perform. We reached a number of milestones. One is the pre-ship acceptance of the core spectrograph in New Zealand in September last year. And one of the things that we did is basically just take the fiber and hold it out of the window and get some sunlight and record the solar spectrum. And that's what you see here. So the MAROON-X spectrum is shown here in blue. And then I took the solar FDS spectrum and broke it down to a resolving power of 80,000, and that's shown in green. And so at first, we got a little bit nervous and said, oh, why is that spectrum looking so different? This is the sun, this shouldn't change. Until we realized, well, the only solar lines that you see are, 4 or so here, that's your sodium doublet. The rest is all water vapor, it's all telluric lines. And it turns out, well, Kidd Peak is slightly drier than the wetlands of New Zealand. So you have shallower water lines there. And the next milestone was then reached in January this year, where we got the instrument delivered and installed in our enclosure in Chicago. So you basically see the main vacuum chamber here, and there's one camera arm for the blue arm integrated and behind here. And maybe it's hard to see that it's basically this little box that contains the fiber input and will house the pupil slicer. As I said, there's a number of components we developed in Chicago. Most important one, the pupil slicer and double scrambler. So the important thing to keep in mind is to have an instrument as compact, as small, delivering you a resolving power of 80,000 on a large telescope. You have to play some tricks, because a 100 millimeter beam on an R4 shell on an 8-meter telescope gives you a resolving power of 20,700 per arcsecond. And so to go to 80,000, you can either make your slit a factor of 4 smaller, which you don't want. The quarter arcsecond slit would be a bit too small, or you have to reformat the light somehow. And that's what we are doing. So instead of having an image slicer, which is kind of the standard approach to this, we said for stability reasons, we actually want to do that in pupil space. So what we want to do is to take an octagonal fiber that brings the starlight from the telescope down to the spectrograph and feed the light into 3 of those rectangular fibers that are 50 micron wide. And so how this comes down is we use a microlens array-based optics that does the slicing and the reprojection on the output fibers. So you have your round telescope pupil, depending on FRD, for example, there might be a central obstruction still left. It's a question of how well in pupil space the fiber will scramble. And then at the end, the output format of these optics will basically slice this in 3. And it looks a little bit funky because it basically crosses some parts of the image, but you have two half moons and basically a central stripe in the middle. And then we put at this image plane, so to speak, we put our rectangular fibers and feed the light back into these fibers. And if we take the fibers and rotate them by 90 degrees and align them this way, we basically form a slit, and we have compressed everything nicely down and get a much higher resolving power without losing too much light. And so the optics are very small. You have a collimator that has a diameter of 2.5 millimeters, so it fits into a fiber sleeve. And then you have a block with two arrays of micro lenses on either end that do the slicing and the re-imaging of the pupil at the back end. On the other end, where you have your image plane, that's where you put the three rectangular fibers. And so that comes down to be not as easy if you want micro lenses that fulfill these requirements and that have low surface roughness. So we went with a molding technique and found a company in Germany who does that. And so this comes out as basically a block made out of two slices with micro lenses on the front and the back. And these are actual microscopic images that we took in the lab of how they look like. So we got a few more lenses extra, just we can move things around if there is some blemish on some of the lenses. We only use 3 out of this array. But so at the input, we project the round pupil on these 3 lenses. And then with the output, we basically get that image you've seen before. So this is the CMAX simulation, how this should look like. And this is the first image that we got from the prototype that we built in the lab last year. And that looks very gratifying, I would say. So we're right now in the process of completing that pupil slicer and maximizing its efficiency. One of the aspects here that are a bit complicating is that it was not possible to actually mold this whole lens block in one. You had to get 2. And so it's our job to align them to about 2 micrometer and bond them together. And so that's kind of tricky, but I think we nailed that. And so at the spectrograph end, we also have to make sure that we get all the fibers nicely aligned, and especially that the rotation angle is roughly correct. And by roughly, I mean better than maybe a degree or so. And so we basically worked with a company in Switzerland called Throughput, who produces glass plates with precision drilled holes using a laser technique. And so we get basically an alignment here that is good to 1 to 2 micron, and in terms of diameter, 1 micron. And then basically etch the fibers, insert them, glue them in, and that's again an actual image from the first prototype device. So you see, it's not quite perfect. There's still some rotation issues here, which I think in the next incarnation of that, we got much better. The problem is when you etch the fibers, you start to not only etch the cladding down, but you start to etch on the core as well. So the rectangular core starts to look like a bone, and then it's hard to actually determine the actual state of rotation if you look at it. So you basically have to, after you etch them, you have to cleave them and then insert them, and then you actually see the proper shape, and you can determine the rotation angle much better. But this is basically how the slit, so to speak, will look like. So you see the fibers here still sticking out of the glass plate. They're then glued in, ground off, and then polished. And that's the result of it. The other thing we built relatively early to understand, like, what will the environmental conditions look like that we put the spectrograph in, is to build an environmental enclosure. So we basically choose to use a meat locker, literally, commercial grade meat locker, as our enclosure. So it's a 10 by 12 feet enclosure, and we added an active temperature control. So there is a temperature bath that is sitting outside, it's conditioning water. It goes inside, and there's a heat exchanger that basically controls the air temperature. And out of the box, without actually playing with the PID values, we basically get 30 millikelvin air temperature stability in that box. Unless you open the door, then this, of course, breaks down. But we also see that we get about 200 millikelvin or so change on the floor temperature. So it's easy to control the air temperature, but it's not so easy to control the temperature of the floor. So that basically went back to saying, how do we insulate the spectrograph physically from the changing floor temperature? And so we have various stages of insulations there that make sure that even if we don't actively control the floor temperature, we don't see that walking through to the spectrograph itself. Wavelength calibrator is something that we have dealt with over the last 2 or 3 years now, and that I'm particularly happy and proud of that Julian and I could make this work. So how this works is it's a vacuum gap etalon, so meaning you have 2 mirrors with a 0-Dur spacer in between, and the distance between those mirrors gives you a certain free spectral range, in our case 15 gigahertz, and the reflectivity of the mirrors determine how sharp the lines are that are coming out of that etalon. And so in our case, we set that to a value of 40, which means that those lines are only 340 megahertz wide and so completely unresolved. And so you basically see in the image here in the middle, this is your etalon in an aluminum cell, and then you have 2 collimator mirrors out here with the fiber feed. And the whole thing goes, again, in its own little temperature-controlled vacuum chamber, because the etalon itself is extremely sensitive to temperature and pressure changes. And so we found that we have to put the whole thing, although it's temperature-controlled, into another box, just to stop seeing like temperature changes in the room walking through. So that's how it looks right now. And then you have a quite complex setup, I would say, above it, which basically guarantees that we can check what the etalon is doing in respect to a standard. And the standard in our case is a rubidium gas cell. So we have a scannable laser that basically scans one of the etalon lines. This is the green curve here, together with the red line, which is a hyperfine spectrum of rubidium. And in reality, we actually look at a slightly wider range to get 3 groups of hyperfine transitions here. And then we use another etalon that is not stabilized at all, that's just sitting there, that gives you this nice ruler that allows you to transfer the known positions of the rubidium lines to the etalon line and measure the position of the etalon with about 4 hertz or so frequency. And so we know where our etalon 0 point is. And then we basically log all the environmental parameters and the measurements we do in a database and have a nice web interface to actually look at in real time over a couple of hours. So this is about 1 day worth of data and just this fraction of the snapshot of what you see, what the etalon is actually doing and what our rubidium standard is doing and all these things. And so we started last year to look into, so what is the intrinsic stability of that? And if you go and look at short time scales, so each tick mark here of 5 minutes, you basically find that you are noise limited to about 130, 140 kilohertz. So this is in megahertz here, which means about 10 centimeters per second. But if you zoom out, so to speak, if you go to longer and longer time scales, so these tick marks are now 2 hours, and now the tick marks are 12 hours, you basically in yellow see that your etalon is doing something very funky, which is like it walks linearly away. And you scratch your head and you're like, so what is that? And then you find, oh, 0-Dur actually ages. 0-Dur is supposed to have basically 0 CTE, but it's a mixture of a glass and a crystal or ceramic type of material. And so over time, there's a phase change and the material shrinks. And this is a very, very minute effect. And in fact, there are papers from the 70s or 80s where people have put 0-Dur on the shelf for 30 years to come back 30 years later and measure the length change. And they had to wait that long. And basically, we see the same thing within an hour because we basically see the 20 centimeters, which is roughly correct for 0-Dur that is 2 years old or so. And we have a linear drift of 20 centimeters per second per day. But now that we know that and we can measure it, we can factor it into the calibration software and say, we know our etalon walks away with 20 centimeters per second. So that's it. We don't have to actively compensate for that in terms of keeping it there. I mean, this can go on for years or decades until we would see any reasonable effect in terms of that the line really physically changes with respect to the rubidium, but we are able to actually track that at that precision. So if you basically look what your Allen deviation looks like as a deviation from pure noise, you basically see, well, for the passive etalon raw data, nothing corrected for, that's the blue line, you basically get down to a couple centimeters per second, but then for longer time scales, so going into the hours, you basically are limited by this linear effect. And if you remove that simply in software and say, now we know what the etalon is doing, you basically get down to this curve, which means that over long time scales, so hours and beyond, we see roughly 5 to 10 centimeters per second, or say 5 to 10 centimeters per second is our precision, which to what we can determine the 0 point of our calibration source. And then if you would go a little bit further and say, oh, we also still see some minute temperature changes at the millikelvin level, and we can also measure that and correlate against it and remove them, we can even do better. But we don't even have to play this, because at a few centimeters per second, we are already there. That's more than good enough. And so this is something that by now is working very well, and that we are now in the process of integrating with MAROON-X. And in fact, this is the first spectrum with our small lab-grade 2K by 2K CCD chip on the blue arm of our etalon. So you basically get, you see individual shell orders, 5 fibers per shell order, and then you see all your calibration lines. And so if you zoom in, that's basically what you see. We're not perfect in focus in that image. It's an early image of the installation. But that's roughly the information density you get now. You basically know for about 500 positions along each order your wavelength. And that will give you a much better handle on this than with, say, the classical Thorium-Argon technique. And so what we did is to see, like, let's compare different techniques of calibrating your spectrum. So at the beginning, while the pupil slicer is not integrated, we have access to all the 5 rectangular fibers, and we can send different light in each fiber. And that's what we did here. So this is a zoom in on 3 shell orders. And in the top fiber, we put a Thorium-Argon lamp. The next 2 are our etalon. And we used one to actually just put a helium neon laser in that gives you one line that is somewhere off the screen here. And the last one is an iodine cell illuminated with white light. And you basically get an idea, like this is a logarithmic scale already, just to make you see where your Thorium-Argon lines is. But there's a huge contrast between individual Thorium-Argon lines here. And there are, regions where they are blended, you can't use them. There are regions where you don't have any. And your etalon is just beautifully the same brightness everywhere. So this is really promising. So this is how this looks like for the full frame. So you see roughly how your Thorium-Argon looks like in comparison to the etalon. And again, logarithmic scale. So we really have already tried to maximize like the Thorium-Argon coverage, but you see at that point even the first argon lines are starting to bleed. So this is one of the big problems if you use Thorium-Argon for simultaneous calibration, that your brightest argon lines are bleeding into your sine spectrum. And so Harps, for example, stopped at some point doing the simultaneous calibration and basically relies on that you take a spectrum before and after each science observation, which is not very good for instrumental efficiency. So we, by necessity, because we are basically funding limited, we started to break up the project in different phases. And so phase 1 was to get the core spectrograph with one arm delivered, to have a 2K by 2K lab-grade CCD chip and test the stability of the system in the lab and make sure that all the components we develop in Chicago are actually working. We are basically at the conclusion of phase 1. So what's left for us is essentially to integrate the Pupil slicer into the spectrograph and to have a longer time series characterizing MAROON-X with our Etalon system and the thorium-argon and maybe even the iodine cell, and continue to improve on our data reduction software. That's a long time ongoing effort. Just before we actually came here, we installed a solar telescope on the roof of the building. So it will automatically send without anything we have to do sunlight down a fiber to the lab. So we can also actually check how the stellar spectrum over time, the radio velocities look like in comparison to our calibrator. So the next development phases are essentially to fully upgrade the system to the desired state, which is having 2 arms, having 2 science-grade large CCDs, and of course to build the telescope front end for Gemini. And the last phase, which we expect to be in early 2019, is to deliver and commission the instrument at the telescope. And so we are making quite some progress here as well. That's the latest optical design for the red camera. We have made quite some changes to that in comparison to the initial design that came with the spectrograph, just to get more back focal distance to be able to, for example, put a shutter in between the camera and the CCD, and to improve on the optical quality of the red arm. And so that's the optical design that is now completed, and we start with the mechanical design, which basically uses the same camera barrel as for the blue arm, but now, of course, updated for the new lenses. And so the build and test phase for the red arm is foreseen for the 3rd quartile in this year, and we hope to receive the camera and integrate it with the spectrograph latest by early 2018. We have also placed an order for the 2 science-grade CCD systems. So this has been something that kept us awake at night for a long time, because going out to 900 nanometers, we not only want to be very efficient, we also want to make sure that we are not limited by effects like fringing, for example, and that's pretty tricky at those wavelengths. On the other hand, we are basically locked in right from the beginning what, in terms of for a given sampling and given instrument, what our pixel size should be for the CCD. So we have to work with 15 micron CCDs, and we need a 4K by 4K. And so luckily we found STA offered us to basically produce a new chip from the same mask that both allows to produce basically classical thin CCD with 30 micron thickness for the blue arm, so really optimized for that wavelength coverage, and then a deep depletion thick device, 100 micron thick, for the red arm that basically gives us, I would say, above 90% quantum efficiency, still at 900 nanometers. 2 separate Archon controllers that are water cooled, their own cryo coolers that are Stirling type cryo coolers and bond shutters. And so this will come as a complete package to us, tested at STA, documented, and we hope that this will integrate in our lab by the 1st quartile of next year as well. So at that point, so in early 2018, we hope to have a complete instrument in the lab, and then we can start on an extensive test series before we actually deliver the instrument to Magellan. Now I made it again. Thank you, Gemini. I knew it. To Gemini, to make sure that the instrument performs exactly at the level that we want it to be, because otherwise it will be a nightmare to fix these things on the mountain. And so our goal is to not deliver the instrument before we are satisfied with it in the lab. And so the other thing we are, of course, working on is a Gemini telescope front end. So the key features for that are, it has to convert the f16 beam to an f3.3 that can go into the fibers. You need a very high performance ADC system, so atmospheric dispersion correction is very important for us. We need basically the same illumination regardless of wavelength. So we basically have a 50 milliarc second RMS goal both for how broadband light hits the fiber and how this is spread over wavelength. And so we have an active guiding system, and we look at the fiber and actively guide on it with a tip tilt mirror. And we have capabilities of actually imaging the pupil to make sure everything is well aligned, and to inject calibration light into the science and sky fibers. So at the beginning of the night and the end of the night, you would do that, then compare whether there are any, so to speak, residual drifts between your science fiber and your calibration fiber in the spectrograph. So if there's that level, there's something like, you know, hard to say what it could be, but temperature shifts, for example, of certain optical elements could give you basically a shift in the intrinsic format along the slit. And so you want to correct for that potential drift as well. So you need to be able to inject calibration light from the ethalon into the science and sky fiber. So the status here is that we have a working optical design, but I'm not particularly happy with it. So we outsourced that and contracted someone with completing the optical design, including the ADC that's currently in the works. We have scheduled a PDR for June this year and hope to have a critical design review in September, from which on we could in principle press the button and order components. And if everything works well, we could deliver and integrate the front end at Gemini in the second quartile of 2018. So the outlook in terms of scheduling to bring the instrument here, looking like that we basically would be ready by the first quartile of 2019 to install MAROON-X at Gemini. I think that's it. Thank you very much.